Let's continue solving homogeneous differential equations. And as mentioned here, our roots are actually repeated and real. And we are to verify that with a certain process later. At the same time, this is very important to note that if ever our roots are real and some of them are repeated, we will be using different types of general solution. In the previous video, we're able to combine a situation where one root is not repeated but the other is repeated. Please review this previous video because it combines the solution, general solution for the first two cases. Here, let's also observe the possibility, but we're not yet sure, so we're going to verify this. The first one here, or first step, is of course to come up with a form of an auxiliary equation of this form here. This is already in a form of equation with differential operator D, so it's easier for us to come up with the auxiliary equation. And it just simply follows like this. Simply substitute m to our D. So it'll be in this form, 4m to the power of 4 plus 4m cubed minus 3m, m squared minus 2m plus 1 equal to 0. This is now an auxiliary equation, and our goal here is to check what are the roots of this. Of course, this is an example of a quartic equation where we have possibility of 4 roots, and then we have a lot of process involved in solving for the roots, one of which is factoring. The other is by using the rational root or rational zero theorem, which P is the factors of your constant 1, so plus minus 1. And your Q are the factors of your leading coefficient 4. So you have plus minus 1, plus minus 2, plus minus 4. But if you're going to look into this, there are 2 times 6. So you have 12 possibilities of roots. There you have 12 possible roots that you can, P over Q values that you can try here to check whether which four of them are our roots. So it will take us time, as well as you have 1 over 4, that's 1/4, 1/2. So you have to deal fractions in here. So that's a little bit what do you call this one, problematic for some. So instead of doing or using the rational root or rational zero theorem, let me use here just a little bit of intuition. Why not simply try to deduce this and think of the first value, the smallest one, smallest integer, which is 1, and simply substitute that in our equation. And let's see if that will really return to 0. And if it is, then 1 is a root. If we're going to substitute that, you have 4. 1 to the power of 4 is 1. Plus 4 times 1 cubed is 1. Minus 3 times 1 squared is 1. Minus 2 times 1 plus 1. Let's check if it's 0. This is 4. This is 4. Minus 3. Minus 2 plus 1. Let's check. This is 8, 9. So it's not equal to 0. Hence, 1 is not a root. Let's proceed to the next value. Instead of moving to 2, let's have the negative value of 1. Okay? So negative 1, you have 4 times the fourth power of negative 1 is positive 1. Plus 4, the cube of negative 1 is still negative 1. You can see that this would be simplified later. So that's what is that is actually the beauty of a negative value. Minus 3 times the square of negative 1 is 1. 2 times negative 1 plus 1, let's check if it's equal to 0. 4 minus 4 minus 3, negative times negative, plus 2 plus 1, you have 4, that's 0, this is also 0, so check. Negative 1 is one of the roots. Hence, our first factor is m plus 1 once you move that on the other side equal to 0. Since we are sure of this already, we can now use the syntactic division to trim down our quartic into cubic function using the select division, cubic equation. Using our select division, the coefficients 4 minus 3 minus 2 positive 1, and you will have here negative 1 as your first root. We have verified that already. And let's also try later to check if negative 1 is one of the roots with that have multiplicity. So you will have here 4 minus 4, as you multiply that, please leave your select division, that's 0. 0 times negative 1 is 0. So you have minus 3 times negative 1, so plus 3, that's positive 1. 1 times negative 1 is negative 1, 0. This here, as a remainder, verifies that 1 or negative 1 is really a root, leaving us with another form, 4m cubed. Then this is 0x squared, so minus 3m plus 1 is equal to 0. Okay, so with this, The next now is to think another number that you can use here. Once you try 1, if m is equal to 1, 4 times 1 cube is 1 minus 3 times 1 plus 1. Let's check if it's 0. 4 minus 3 plus 1. Please don't be confused with that. Some of us will still have problems with that. We cannot do this first and say it's equal to 0 because 4 plus 1 is 5 minus 3, not equal to 0. Okay, please take note of your MDAS as well. So it's 1 is not possible. Same as earlier. What if we try negative 1? So 4 times the cube of negative 1 is negative 1 minus 3 times negative 1 plus 1 is, let's check if it's equal to 0, negative 4. Negative times negative is plus 3 plus 1, and obviously that's equal to 0 now. M, which is negative 1, is also another root, but it has been already identified here. So we have identified already repetition on our roots, and they are both real. So it already fits the claim earlier. So after this, since negative 1 is another root, so by static division, 4, okay, take note of this. Very crucial in static division. Do not write minus 3 and 1 here, leaving the 0, because you don't have m squared here. You should place here something to capture that. Minus 3 and 1, you have your negative 1. Because if you will leave this out, then your answer will be wrong. Take note, this is the result earlier, 0m squared, so we'll have that. Okay, so 4 times negative 1 is negative 1. See, if this is here, that's another value. But if it's 0, we place 0, then of course it is now correct. Minus 1. Negative 1 times negative 1 is, minus 4 here. So minus 4. Not my bad. Minus 4 times negative 1 is positive 4. You have positive 1, negative 1, 0. Again, an assurance that your second root is correct. Our form now is 4 m squared minus 4m plus 1 equal to 0. This is actually the perfect square trinomial. Our roots are actually 2m minus 1 and factors minus 1. Okay, what if, sir, I don't know how to do that. So of course, let's use AC way. A times C. Your A is 4 times 1. 4. What are the factors of 4 when added will result to the middle coefficient of minus 4? So you can have 4 times 1. No. Negative 4 times negative 1, no. 2 times 2, no. Negative 2 times negative 2, that's positive 4. And when you add them, that's positive 4. Hence, you will have this in our solution, or our entry here. But we are not going to come up with m minus 2 and m minus 2. Take note of this. Or we are inserting concepts of factoring as well. Because if we're going to use the FOR method, it will not return to 4. Right? 4, because this is 1 times 1. So what you need to do here is this. Simply copy our coefficient 4, 4m, and then minus 2, 4m minus 2. So you'll have here 4m minus this, and 4m minus this, as you have 4. But of course, when you have 4 times 4, that's 16. That's not 4. Hence, you can simplify this further, factor out 2, factor out 2. You will have 2m minus 1, 2m minus 1, equal to 0. Similar to that. Please review your factoring as well. So finally, we have verified our 4 factors. You have m plus 1. Here, because this is our root, this is also another m plus 1. Then you have 2m minus 1 and 2m minus 1. Hence, this given auxiliary equation is equal to this. M plus 1 times m plus 1 times 2m minus 1 times 2m minus 1 equal to 0. Our first root is negative 1. Our second root is also negative 1. Multiplicity of 2. Our third root, 2m is equal to 1. M sub 3 is 1/2. Okay? And then our fourth root, 2m minus 1 equal to 0. Similar to this, our fourth root is also 1/2. Multiplicity of 2 as well. So we have situation here. Our roots, we have two types of two roots. Negative 1 and 1/2. But both of them have multiplicity of 2. Hence, it fits to this criteria here. Okay. So how do we show our final solution now? it follows this pattern for our general solution for situations like this. Y is equal to e to the power of mx times c sub 1 plus c sub 2x plus dot 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 plus c sub n x to the power of n minus 1, where these are the number of roots, a number of times the root is repeated, and here would be your first root. But since we have two roots of the same repetition, so we have two types or two forms of this. Here will be our solution. Okay, listen to this. E, our first root is negative, so negative 1x times c sub 1 plus c sub 2 x until just here, because there the root of negative 1 has a multiplicity of 2. But since we have another roots here, so we simply take plus e to the power of our second root, which is 1/2 x times the same process, but we will no longer use c sub 1 and c sub 2 because they're already used. So you have c sub 3, don't worry about that because they are arbitrary constants, plus c sub 4 x. This is the solution for our given differential equation earlier. You might want to distribute this if you would like to, but I'm okay with that. That's already the final answer for me. Okay? So this is the answer to this given situation. Thank you very much for watching.